In this video, we're going to move beyond our discussion of runtime organization and begin talking about code generation. And in this first, this will be quite a long series of videos on code generation. We're going to talk about the simplest model for code generation, which is called a stack machine. So in a stack machine, you might guess that the primary storage is some kind of a stack, and you would be right. In fact, the only storage that a stack machine has is a stack. And the way a stack machine works is that it executes an instruction. All instructions have the form. There's some function of some arguments, and they produce one result. And what that does is it'll pop n operands from the stack. So the arguments a1 through an are stored at the top of the stack. It will then compute the function f using those operands, and it will push the result r back on top of the stack. Okay, so let's take a look at a simple example. Let's see how we would compute 7 plus 5 using a stack machine. So we would have our stack, and initially the stack might already have some stuff on it, but we don't care what that stuff is. And so to execute 7 plus 5, what we would do, well, first we will have to get the 7 and the 5 onto the stack. So those would get pushed onto the stack, and we'll say more about how that happens in a minute. But let's say that 7 and 5 are both on the stack. And so now we want to compute the addition of 7 and 5. So addition takes 2 arguments. So we would pop the 2 arguments off the stack. Okay, we would wind up with the 5 and the 7 popped off the stack. We would perform the operation plus, and then the result would get pushed back onto the stack. So this would be equal to 12, and then 12 would get pushed back onto our stack. Okay, and now notice that I did indicate that there might be some other stuff on the stack already. Let me just give that stuff a name. And let me talk about one very important property of the stack machine. So notice that when we evaluated 7 plus 5, we wound up in a situation where the result of that operation was on top of the stack, okay, and the initial stack contents was unchanged. This stack, the stuff that was below the arguments that we were interested in, didn't get modified. Okay, so it survived through all the operations unchanged. And this is an important property of a stack machine that we will exploit. And the general, and just to say what the general property is, when you evaluate an expression, the result of the expression will be on top of the stack, and the contents of the stack prior to beginning evaluation of the expression will be preserved. So now let's think about how we could program a stack machine. So let's have a language with just 2 instructions in it. We can push an integer onto the stack, and then we have the operation add, which will add the 2 integers at the top of the stack. And now let's take a look at this program, which pushes 7 and then pushes 5 and then does an add. And so let's think about how this program would work. Okay, so we have our stack contents, and now the first instruction is to push 7. So we wind up with a 7 on the stack, added to the stack, and now we push 5. Okay, so in the next step, we'll have 5 and 7 on top of the stack. Then we'll perform the add, and that will pop these 2 elements off the stack and add them and push the result back on. And we'll wind up with 12 on the stack. And again, the original stack contents are preserved. Now, one interesting property of stack machine code is that the location of the operands and result is not explicitly stated in the instruction. And that's because these instructions always refer to the top of the stack. And this is in contrast to a register machine or register instructions that explicitly name where they take their operands from and where they put their results. So for example, you might be familiar from seeing some machine code or assembly code in the past that an add instruction might typically take 3 registers, 2 for the arguments that are 2 for the register arguments that are going to be added together, and 1 for the destination for the result. Whereas in the stack machine, we just have a single word add and no explicit naming of the arguments, because it's fixed where the arguments will come from. The arguments will always be popped from the stack, and the result will always be placed back on top of the stack. And the interesting property here is that this leads to more compact programs because you have to say less in the instructions. The programs themselves are actually quite a bit smaller than register machine programs. And this is one of the reasons that Java bytecode uses a stack evaluation model, because it leads to more compact programs, and especially in the early days of Java, when it was fairly expensive to ship these programs around the internet, to download them, having very small compact code was a good property. Now you might wonder, why would we prefer a register machine? And the answer is that register machine code is generally faster because we can place the data exactly where we want it to be. We will generally have fewer intermediate operations and less manipulation of the stack, pushing and popping stuff to get to the data that we want. And it turns out that there is an intermediate point between a pure stack machine and a pure register machine that's interesting. This is called an n-register stack machine. And conceptually, the idea behind an n-register stack machine is just to keep the top n locations of the stack in registers. And the particular variant of the n-register stack machine that we will be particularly interested in is the one-register stack machine, because it turns out that you get quite a bit of benefit by even having a single register that's dedicated to the top of the stack. This register is called the accumulator. So the dedicated register here is called the accumulator. It's called that because intuitively it accumulates the results of operations, and then all the other data lives on the stack. So what is the advantage of a one-register stack machine? Well, let's think about the add instruction and how it works in the pure stack machine. So in the pure stack machine, what is the add instruction going to do? Well, it's going to pop two arguments from the stack, say 5 and 7, and it's going to add them, right? And then it's going to put the result back onto the stack. And let's just name the rest of the stack contents there. And that requires 3 memory operations. Have to load 2 arguments and then store 1 result. But in the one-register stack machine, the add operation actually does a lot of its work out of the one register. So the one of the arguments is already stored in the register because that's conceptually the top of the stack, and the result will be pushed back onto the top of the stack, which again is just the accumulator register. So here, one of the arguments and the write are both taken from registers, and there's only one memory reference to get the second argument from the portion of the stack that's stored in memory. So in general, let's think about how we would evaluate an arbitrary expression using a stack machine. So now this isn't, I should say, just stack machine code like we were looking at before. This is not just a sequence of bytecode level operations. This is actually a full expression, as you might find in COOL. So there are other complex expressions nested inside of some operation. All right? And so if we have an operation that takes n arguments, and those arguments are expressions that themselves need to be evaluated, here's a general strategy for doing that with a stack machine. So for each of the sub-expressions, each of the arguments in order, we're going to evaluate it recursively using the same stack machine strategy, and that will end up putting the result, when we evaluate EI recursively, the result will be in the accumulator. Okay, so the result is in the accumulator. All right. And then we're going to push that result onto the memory stack. So we're going to take that result and we're going to free up the accumulator and save it on the stack, the portion of the stack that's in memory. Okay. So we do this evaluating the sub-expressions for the first n-1 arguments. So everything except the last one. Okay, we're going to use this same strategy. For the last one, for en, we just evaluate. We don't push the result on the stack. That just means that the result is left in the accumulator. Okay, so now we have one of the arguments of op in the accumulator, the last one we evaluated, and the other n-1 are on the top of the portion of the stack that's in memory. So then all we have to do is we pop n-1 values from the stack and combine it and then compute op using those n-1 values plus the value in the accumulator, and we store the result back into the accumulator. Okay, so that's the general strategy for evaluating an expression using a stack machine. So let's do this now for a simple example. Let's take our same example that we've been using, and let's evaluate the expression 7 plus 5. So how did we do that? Well, we're evaluating a plus expression, and that takes two arguments, two expressions, and so we had to evaluate each of those. So first we evaluate the expression 7. Let me draw our stack here. Okay, so we have our initial contents of the stack, we have our initial accumulator, and so now we're evaluating 7. Okay, and of course a constant will just evaluate to itself, and the result is stored in the accumulator. Okay, so that's the first step after evaluating 7. And now, because that's the first argument to plus, it has to get pushed on to the stack, the portion of the stack in main memory. So now we have a situation that looks like this. All right, and of course the 7 is still in the accumulator, but we're about to overwrite it. We're not going to use that value again, because the next thing we're going to do is evaluate the second argument to plus, and that happens to be, in this case, also a constant expression 5, and so that will get evaluated and then stored in the accumulator. Okay, so that will overwrite the 7. Okay, so it'll be a 5 there. All right, and now we've evaluated both arguments. Okay, and remember, in the case of just having two arguments, the first argument gets evaluated and saved on the stack, so it doesn't, so we don't lose the value when we evaluate the second argument. And the second argument, since it's the last one, we can just leave in the accumulator. And now we actually evaluate the plus. Okay, so we do the accumulator gets the accumulator plus the top of the memory stack. So in this case, that results in adding 7 and 5. And we wind up, and of course we pop the argument from the memory stack. All right, so we have just the original contents there, and now the value 12 in the accumulator. So as I think you can see from the example, the invariant that we're going to maintain with a stack machine is that after we evaluate an expression E, the accumulator holds the value of E, so the result of evaluating E winds up in the accumulator, and the stack is unchanged. Okay, so the stack, the memory portion of the stack, is whatever it was before we started evaluating E. And this is a very, very important property. Expression evaluation preserves the stack. So now let's look at a more elaborate example, just slightly more elaborate. 3 plus 7 plus 5. And the interesting thing about this example is that now one of the arguments to the outer plus is itself a compound expression, and so that will have to be evaluated recursively as part of evaluating the entire expression. So let's see how this works. So the first thing that's going to happen, we're evaluating the outer plus. We're going to evaluate the first argument of that plus. That's just the constant 3, so that will get loaded into the accumulator. Okay, that's the result of evaluating 3. And now, because it's the first argument to the plus, we have to save it for when we get around to evaluating the addition itself, so that result gets pushed onto the stack. And now we're going to evaluate the second argument to the outer plus, and that itself has two arguments, and the first argument to the inner plus is 7, and so that winds up getting stored in the accumulator. That's the result of evaluating 7. And then because the inner plus has two arguments, and we have to evaluate the second argument to the inner plus, the 7 has to get saved on the stack. So now the stack has 7, 3, and whatever it had before we started. Next, we're going to evaluate the second argument to the inner plus. And so evaluating the constant 5 will result in 5 being loaded into the accumulator. And now we've evaluated all the arguments to the inner plus. Okay, and so we know from our stack discipline that the last argument is in the accumulator and the first argument will be on top of the stack. So the next thing that will happen is that we'll pop that second argument from the stack, add it to the accumulator, and store it back into the accumulator. And so now we have the result of the inner plus in the accumulator. We also have to pop the 7 from the stack. Okay, and finally, now we've evaluated the second argument to the outer plus, and so now we can perform the outer addition. And what does that involve? That takes the stack contents and adds it to the value that's currently on the top of the stack, which is the value 3, which is what we saved a long time ago now to remember it from when we wanted to do the outer addition. And we wind up, after we pop the stack, with 15 in the accumulator. That's the result of the entire expression. And notice that it's the same stack that we started with. Okay, so evaluating this entire expression resulted in the result being in the accumulator and the stack being unchanged. Okay, and if you look at the sub-expressions, you can see that the same thing happened. So let's take a look at the evaluation of 7 plus 5. So where did that take place? Well, that started here. Okay, started at this instruction. And it lasted down to here. And you can see that the evaluation of 7 plus 5, which encompasses these 5 expressions, resulted in 12 being put on top of the stack. That's the result of 7 plus 5. And it didn't affect the contents. It resulted in 12 being placed in the accumulator, and it left the stack unchanged from where it was when the evaluation of 7 plus 5 began. So here's where it began. And the value we had saved, 3, was on the top of the stack. And when we're done evaluating 7 plus 5, indeed, again, the value 3 and all the other stuff that was there before are still on the stack.